Hello everybody, this is Marco D'Ambros. That is the theory of how to build a bulge system with a matrix. So I made the first video where I show you how to do it in Bifrost, but I would like to go a little bit deep and try to explain the theory just to have like a better understanding what we are doing. The system is pretty simple, but I think it deserves to have some explanation. So what we are going to do, we have a matrix here, we have a geometry here with every vertex. The process we're going to do, we are going to multiply the inverse matrix of our matrix, the inverse matrix with every vertex position. In this way, we're going to compute a local vector that is going to our matrix to our vertex position, like this. So let's write down. So we are going to have our vertex local. It's equal to our vertex position multiply our inverse matrix. This vertex is so we have now this our vertex lock. Our vertex lock, if we are going to compute the magnitude of this one, so the length, it's our magnitude f lock. We are going to define if this vertex is now inside or outside our imaginary sphere of radius. So we can say then is our magnitude if is minus our radius, like this one for example, it's inside to our sphere. So we want to collide, we want to push this one away. And what is the best, like how we are going to push it? This is very simple. We are going to normalize the vector. So normalize the vector is kind of like forcing the vector to have length equal to 1. So if we, for example, we have a vertex, let's actually do, let's create a collision actually, a proper one. So we can write a better example. Let's increase it with the radius just to have a slightly okay difference. So if you see the video, the red dots are the vertex inside the sphere or the collision, and we have already the collision here. So what's happened? Let's say we have our matrix here, we have our geometry here, we have our vertices, let's say create few. So we have our local vertex there. In these two, v1 and v2, we the length of this vector, localized vector, is minus then our radius. Let's say 1, but like minus our radius. When we force it, when we normalize it, we are going to, let's say, bring back the length to our radius here, to 1. So technically, we are going to normalize our vertex local and multiply by our radius. So with these steps, with the normalize of this vector, we are projecting our mesh, our vertex to this imaginary sphere. Like I show you, we can literally move in this one here, and we are going to have a projection. Let's do the projection part. So if we are going to do this one, very good. So now we have literally project the plan to our sphere. I'll show you better. If I move this one, you see, our plan is literally projected on our matrix. Actually, this can be useful in a lot of other situations. Well, a lot in other situations. Maybe a lot is a big word. So here you go. So yeah, so where we are at the moment, we are getting our vertex. We are pushing to 1. We normalize to 1. So now we have our final shapes. The thing we have to do, we use this condition to define which vertex we want to push or not. And in the example, you can see here this if is a if our length is minus our radius, we're going to push. We're going to switch between the not push and the push at one. Here we go. So like I see, the theory is very simple. It's actually three literally steps. We are going to create our local vector. We're going to check if our magnitude is minor and is less than our radius. And we are going to normalize the vector to push or project to our sphere. One of the things that I want to stress out is please go to check the homogeneous coordinate because that is a very important is a very important concept and is going to change your life. It is going to work with vector or point and matrices. You can see here we have a lot of conversion because we have swapped between a matrix multiplication and a vector operation like a normalize. So we want to swap between 4 and 3 all the time. And like I showed you before, let's see again. So if I come back to the normalized one, the projection one. So for example, in the projection, if we are going to change this value from 1, then is our point, to the vector, is literally change the, let's go change the way then we see the result. And so you can create, you can have, it's easy to make a mistake if you forget to swap, to create a vector 4 with a W1 if you're working with the matrices. So thank you very much to follow on this very quick theory about it. Have a lovely day.